Okay. Now we talk about sensors. Just a brief introduction on the concept of sensors, and then we will look in some more detail and at how a few sensors that are, for example, at the moment pretty common in smartphones operate. So we shall start with some generalities about sensors, so that we can also define their main properties that will allow us to, let's say, compare different types of sensors of the same kind. So a sensor is a sensor is a device which receives a stimulus and responds with an electrical, basically because we are interested in electrical sensors, with an electrical signal. Okay, let me put electrical between parentheses because it's not part of the definition of sensors. The point is that we are interested in, let's say, sensors in electronic systems, and they have to provide an electrical signal. So here the three keywords are device. A device basically is something, we can call it a system, a thing in general, which has a function. So it's a system, basically any system which has a function is for us a device. The stimulus that the sensor receives, this device receives, is basically the quantity or the condition that we want to measure. So the stimulus is the quantity, the physical quantity, or the condition that we want to measure. So by quantity we mean a physical quantity, can be the temperature, the acceleration, the angle, or the condition is something like is the door open or closed, has the pen touched the tablet, or something similar. And then the signal is, if we talk about electrical signal, basically is a quantity which can be, let's say, a classic electrical quantity. For example, the voltage, or a current, or a charge. Those are the quantities that we typically want to measure. The other thing which is useful to highlight is the exchange of energy and information between a sensor and let's say a larger system to which the sensor is connected. And there are two flows which are always present. One is an information flow, and typically this information is carried by the electrical signal, and together with the information flow we always have also an energy flow. From a physical point of view, they information and energy flow together, in the sense that, for example, an electrical signal carries both information and power. So they are very often the information flow and the energy flow, they are very often connected with the same process. As an optional situation, we also have an energy flow in the other direction. This is, let's say, optional. It really depends on the sensor, because in many situations we need to provide some power supply to a sensor in order to let it operate. For example, if the sensor, of course, is a camera, of course we need to provide a power supply to the camera. This is not true for all sensors. Okay, regarding some nomenclature, a word which is very often found together with the sensor is transducer. Transducer in Italian would be trasduttore, senza la N. And basically, a transducer has a different definition with respect to that of a sensor, but with some similarities, because a transducer is a device, again, which transforms information from one form of energy to another. Okay, of course, according to this definition, a sensor is not the same thing as a transducer. So a transducer, again, let's consider the definitions pretty carefully, because of course definitions say a lot and we must use properly the different terms. So a transducer is again a device, so a system with a specific function, and the function is to transform information from one form of energy to another. In the physical world, information is always connected to energy, and the typical way to extract information from the physical world is to transform this information from one form of energy to another. In the specific case, to any form of energy, to electrical energy, because in the case of electrical energy, we can operate with electrical signals and then we know how to proceed. So for example, a photoelectric sensor transforms the information which is encoded in light, so in one type of energy, to electrical energy in an electrical signal. And this is required in order to obtain the sensing operation. Of course, it's not enough, because to obtain a sensor, we need to transform this information, which is encoded in an electrical signal, in an electrical signal that can be actually transmitted and used by the larger system to which the sensor belongs. So in a typical situation, what we have is something like this. We have, let's say, the stimulus, which is the quantity that we want to measure in a given form of energy. Then we have, for example, a first transducer, which transforms this information in another form of energy, but of course preserves the information. Then we can have a second transducer, which transforms this second form of information, this information from the second form of energy into finally an electrical signal. And then we need some electronics for signal conditioning and transmission. And at the end of this block, we have a signal, which is actually, let me write it clearly, usable, which means it can be used, it can be transmitted to the larger system. So for us, the sensor is this more complex system. So the system which comprises all the various transducers which are needed in order to obtain an electrical signal, plus all the electronic circuits which are required for signal conditioning and transmission. By the way, probably you have never heard this term conditioning. What does signal conditioning mean? Signal conditioning means the processing of a signal which preserves all the information and enables the signal to be actually transmitted. So typically part of signal conditioning is amplification, is filtering, is sometimes analog to digital conversion, and so on. So all the processing which is required in order to have a signal ready to be transmitted. That is signal conditioning. You have to assume that even if you, at the output of the last transducer, you have an electrical signal, this electrical signal is typically weak, is rich of noise, and therefore is not really usable for by other systems. So let me write just as an example: filtering, amplification, AD conversion, other processing. Okay. For example, we shall see it in some more detail later, but if you consider an accelerometer, which is a pretty common sensor, an accelerometer wants to measure an acceleration, of course, and the way the acceleration is measured is that typically you have a first transducer which transforms the acceleration, which is your stimulus, into a displacement, so into a variation of position. Then there is a second transducer which transforms this displacement into a variation of capacitance. And then there is a third transducer which transforms this variation of capacitance in an electrical signal, in a voltage. And then finally this voltage is amplified, filtered, transformed into a digital signal, and then of course at that time it can be transmitted. Okay? So the output of the accelerometer is a digital number corresponding to the acceleration, but there are a series of several transducers plus all the electronics in order to obtain the final quantity. Of course, this is just an example for me. Now, we of course will look into the operation of accelerometers more in detail. Okay. Now, another concept which is well, pretty easy to understand is the concept of actuator. And there's a pretty easy way to consider an actuator, is that the actuator is the inverse of a sensor. It's basically is a device, again. Let me just show you the definition. Is a device which receives as input an electronic signal, an electrical signal, and provides a stimulus at the output. This stimulus is a specific physical quantity or variation of a physical quantity that we want to have at the output. And so the way an actuator is obtained is by having really the inverse chain with respect to a sensor, because actually what we have is a electronics let's say for signal conditioning, let's say, and actuator driving, because now the signal must drive no actuator, let's call it transducer driving. And then we have a series of transducer 1, transducer 2. So here we have the stimulus, and this is the signal. The actuator is this complete system. Okay, of course, here the signal is electric, so it has an electric form of energy, and then of course the number of transducer is it can be 1, 2, or 3. It's not really important. This 2 is just an example. Okay, but at the end we need to provide the stimulus. Now the role of the electronics in the actuator is different than in the sensor, because typically you have a good signal coming from for example, a microcontroller or a microprocessor. What we need to do is to condition the signal and to provide to the signal sufficient power so that the signal is able to drive the transducers. So, for example, let's assume that we want that the actuator is a motor. Okay, a motor for let's say positioning arm. What we need to do is to transform the signal from digital to analog, and then to amplify it sufficiently, and to typically let's say encode it in a way that allows us to drive a motor. So there is a DA conversion, then there's some amplification, and also some proper encoding to be done. Okay. In the case of sensor, one of the main role of the electronics is to actually extract the signal from the noise and provide a proper amplification in order to increase the signal to noise ratio. In the case of actuators, the problem is of course different, because the signal is typically pretty good. Okay. So the typical situation in which sensors are used is a so-called data acquisition system. So let's assume that we have a situation in which we have on one side an electronic system, on the other side we have the world, the physical world that we want to measure. The world in generic terms, it can be, if we're talking about an environmental data acquisition system, the world can be an environment. If it's an on-body data acquisition system, the world can be, let's say, our own body. It really depends on the context. And let's assume that this is the so-called signal conditioning interface, which is basically an interface that separates the electronic system from the rest. This is a very generic term. This interface can be the interface of the silicon chip if the electronic system is all integrated in one single chip, or it can be a board, it can be the package of the whole system. It can be, for example, the interface of the external interface of the phone if the electronic system for us is the phone. It's a very generic description in this case. The point is that on the right of this interface we have a completely electronic system. So all signals are electric, and we only describe the operation in terms of voltages, currents, and charges on the right hand side. On the left hand side, on the other hand, we can have some other physical quantities. Okay, so it's really separation of concepts. And this is useful for me in order to show you what are the typical types of sensors that we can have. We can have sensors like this one that are not really in contact with the external world. These are the sensors that we would call remote sensors. For example, a camera can be a remote sensor. And before the signal enters the electronic system, we need a proper interface. The interface can be, let's say, a classical interface for electronic systems, a classical standard, as we have. Many are standardized, others are not, but it's not important. Really, we decide what is the interface between the internal electronic system and the outer world. And then we can have some contact sensors. This would be these contact sensors can be of different types. For example, some of them can already provide the signals in a form which does not require a specific interface, so that they can enter directly into the electronic system, or some other can actually require an interface. So if you consider this situation, the sensor 2 and 3 do not have an independent power supply, so they are passive sensors. Actually, also sensor 1, in the way in which I have drawn it, is a passive sensor. Okay, so passive means that they do not need external energy from the electronic systems in order to work. Let's assume that instead the last contact sensor is an active sensor. which means that of course it needs an actuation circuit which receives input from, let's say, a microcontroller here. So the actuation circuit provides actuation, for example, power supply at least, to the sensor, and then the sensor can provide back the information. For example, let's assume that it does not need a specific interface. Of course, we can have also actuators here. They can directly act on the world, and of course also this actuator must be driven by a microcontroller. So this is a typical situation. Here, all these sensors data which are coming into the electronic systems are typically multiplexed. So we have a multiplexer, a MUX here at the input, and we can have, if the signals are in analog form, we can have a single analog to digital converter that transforms the data into digital data that can be sent directly to the microcontroller. So this is not required. This is only required if signals are analog. Okay. And finally, to conclude, the microcontroller, of course, has to communicate with some memory banks and with some peripherals. This is a relatively, let's say, abstracted description of a data acquisition system. You should consider that this is pretty common now, and also that, for example, at present, many microcontrollers for sensing applications, especially in the context of the so-called Internet of Things, basically have in a single package the complete electronic system. So there are, and this is pretty common now, there are several inputs, several analog inputs. Inside the chip there is a multiplexer and an analog to digital converter, so that the data can be directly, let's say, read by the microcontroller. And of course, in the same chip we also have some both dynamic and non-volatile memory, and some control of peripherals. So depending on the application, all things that I have represented in the electronic systems can be in a single chip. And in this context, the interface really need to adapt the signal to from the let's say type of electrical signal that we have at the output of the sensor to the type of electrical signal which is required at the input of the multiplexer. There can be some adjustment in terms of total range of the signal or maximum voltages, maximum currents, and so on. Okay, this would be an active sensor. Okay, finally, to conclude on this brief description of the main definition of sensors, we can have some sort of classification which actually can be done on the basis of different categories. We have seen one of them, which is passive-active, passive or active. That I already illustrated. Basically, passive sensors, you do not need external energy to operate the sensor. In active sensor, you need to provide an external source of energy to the sensor in order to operate it. But of course, there are other possible classifications. One is, of course, on the basis of the conversion phenomenon. The type of physical phenomenon which is exploited in order to convert the stimulus into the signal. This type of the possible categories really depend on the type of sensor, but it's of course a significant, very common way of classifying sensors of a specific type. And in addition to that, a useful classification is between absolute sensors and relative sensors. And this is not obvious from the point of view of definition. An absolute sensor provides a measurement with respect to an absolute scale. And a relative sensor provides a measurement with respect to let's say, relative condition. Most position sensors are relative, because they measure, for example, the position with respect to a reference point. In that case, it would be a relative sensor. Absolute sensors are well, basically of different types. Well, for example, in the case of temperature, there are some physical mechanisms which provide you a temperature in absolute terms, and some other physical mechanisms which provides a temperature with respect to a reference temperature that you might have defined. That is also important to know, depending on the type of application. Okay. I would like to continue with a few other definitions of properties of sensors, which are, let's say, pretty well known. They are typically common terms, but in practice, they, let's say, in the natural language, they would be very common terms with an intuitive meaning, but in the context of measurement and in the context of sensors, they have a very specific meaning and a very specific definitions, so they must be used properly. One of these property is the sensitivity. In Italian, it is called very often sensibilità of a sensor, but also very often it's let's say a term which is left in English, just to let's say stress the fact that it has a very specific definitions. Is not let's say the common meaning of the word in Italian. So how do we define the definition? Let's assume that we call with small s the stimulus that we want to measure, and with big S the signal. And of course we have a function which provides the signal as a function of the stimulus. Let's call this function f. This is the transfer function. This is the transfer function of the sensor, or of the transducer. This is really something which can be applied to both the sensor and the transducer. Please note that this definition of transfer function is not the transfer function that you have seen in signal theory. Okay, it does not depend on frequency. You have a quantity, well-defined stimulus at the input, and a corresponding well-defined signal at the output, and of course the signal must be a function of the stimulus. So this function is generally non-linear, and we can plot. Of course you would like to be a monotone function, so that for every, if you have a single signal, you know exactly what is the corresponding stimulus, because this is the information that you want. Okay, f to the minus 1 must exist, so it must be invertible, which is let's say which is the same as saying that f is monotone. For a simple function, the fact that f is monotone is sufficient. So because if the inverse exists, I can compute the stimulus once I know the signal in this way. Okay, let's assume that f is like this. So it's a nonlinear function in general, and for a given for a given value of the stimulus, let us call S a bar, then we can define the sensitivity in this way. The sensitivity is simply the derivative of the transfer function in S bar. So is defined as the derivative of S with respect to small s in so it's basically the f over the s computed in S bar. So let's say in intuitive terms, the sensor is sensitive if a small variation in the stimulus yields a large variation of the signal. So if this derivative is large. Actually, what is more used is the so-called relative sensitivity, which is simply 1 over s times ds over the small s in corresponding of s bar. Basically, the relative sensitivity is the sensitivity divided by the signal. Okay? Please consider that this quantity has to be specified for a specific value of the stimulus, because in general the transfer function is not linear. Okay. It's important to compare when one compares two different sensors for the same type of stimulus. One very important parameter with respect to what the two sensors are compared is exactly the sensitivity. Typically, the sensor that has the highest sensitivity is better. It typically costs more, and it is to be preferred. It's not the only property that is important, but sensitivity is for sure an important parameter. So another concept with respect to sensors that is important is the so-called calibration. Calibration also is a relatively simple concept. The fact is that sensors are objects that are fabricated, and therefore there are fabrication tolerances. Not all pieces are identical, and because of fabrication tolerances, the actual transfer function is different from the nominal transfer function. Okay, so the nominal transfer function is the transfer function I think I have. Okay, so the one, for example, which is given by the data sheet. And the actual transfer function is the real transfer function of the sensor. And so, for example, I can have, let me give you the same example as before. Let's assume that this red line is the nominal transfer function. But instead, because of fabrication tolerances, the one sensor that I have in my hand has this blue transfer function. Of course, there is also some variability in the sense that the actual transfer function can vary from sensor to sensor, right? Okay, what's the problem with this difference? Is that, of course, this difference leads to an error, because let's assume that this is the stimulus that I want to measure, the actual stimulus here. The actual physical quantity, let's assume it is this one. Then I obtain, because the actual transfer function is the blue line, I obtain this signal, and since I assume I have the nominal transfer function, I interpret this signal as this stimulus. Okay? And therefore this difference is the error that I make. Okay? So to summarize, the maximum difference between the actual transfer function and the nominal transfer function gives me the maximum error that I can make for the measurement. Now, the calibration process basically has the purpose of making the actual transfer function as close as possible to the nominal transfer function. And you can obtain it in two different ways. One is to modify the nominal transfer function in order to make it closer to the actual transfer function. And how do you do that? You typically need the nominal transfer function in order to perform the inverse operation, and you have the nominal transfer function as a function with some coefficients, and then you calibrate, you adjust the coefficients that you have in order to modify the nominal transfer function and to make it as close as possible to the actual transfer function. So this is just a sort of coefficient calibration. I adjust the nominal transfer function. So we modify the nominal transfer function to fit the actual one. Just think about it. This is something that you need to do for every specific sensor, and it's very common. Typically there's a sort of calibration procedure which is done in the factory or during a calibration phase in the operation of the sensor, during which some coefficient which define the nominal transfer function are modified in order to match the actual one. So the calibration procedure, of course, is done in many different ways. The important part is that you need an independent way of knowing the stimulus so that you can check what is the electrical signal that you have, and then you can adjust the nominal transfer function in order to move it closer to the actual one. So you do it for a few different values of the stimulus and adjust the curve, let's say, consistently. This is, let's say, sometimes it's done in a factory, sometimes it's done periodically. For example, for this tablet, it's very common. If you have a tablet, you typically do a sort of coefficient calibration by every now and then checking the angles of the tablet. So you know the position, and you check the electrical signal, and therefore you adjust for the 4 points the nominal transfer function to the actual transfer function. Okay, and in this situation, the more complete the calibration procedure is, which means the more coefficient you have and the more stimulus you use for the calibration, the more accurate the calibration is. Okay, this is one possibility, but there is one other option which is also very common, is the so-called trimming. And the trimming is the opposite procedure. What you do is you physically change the transducer in order to modify the actual transfer function and to make it closer to the nominal transfer function. And that is also very common. So we physically change the transducer in order to modify the transfer function. Okay, also that is pretty common, and of course you can imagine that the trimming procedure is some physical process that must be done for every piece, for every sensor, and of course it increases the fabrication costs. And that is pretty common for the more complex types of sensors. In those cases, you really need to modify the trimming. One sort of soft trimming that is done. Let me just go back to this. Oops. Yeah, to this small definition of transducer. So no, the transducer. So you can do the trimming acting directly on a transducer. An easy way of doing the trimming, a sort of soft trimming, is to act on the electronics for signal conditioning, to change the electronics for signal conditioning in order to modify the transfer function. Because in this case, you just need to, let's say, change some electrical quantities. You typically have some analog or digital non-volatile memories that you can change and adjust in order to modify the actual transfer function. The transfer function is from the stimulus to the signal, so you can change any of the block in order to modify the total transfer function. Of course, let's say if the trimming acts on the electronics is a sort of is a soft trimming, in the sense that you typically have to modify some content of registers, and that can be done, let's say, by software. You don't need to actually physically touch the sensor. Okay, just to continue on the properties. One very critical one is the so-called accuracy. And the accuracy is defined as the highest deviation from the true value of the stimulus. So, for example, you can have a nominal transfer function like this, just as an example, I took a line, but it's really not required, and we can have, let's say, an actual transfer function which is close to the nominal one, but is a bit different. Let's say this is the actual transfer function. And then you need to, in order to evaluate the accuracy, you need to check when the difference at the constant signal is maximum between the actual transfer function and the nominal transfer function, so that you can identify the, let's assume it is this one, the maximum error you can make. So this is the highest deviation from the true value. There is this concept of true value in measurement. The true value is the it's as in let's say in common language the actual value of the stimulus that I want to measure. So this is the maximum difference, and this is the accuracy of the sensor. So the maximum difference from the true value, let's assume it is this S bar, and the value that I measure is S star. The whole point of calibration, as you have seen, is to reduce the accuracy. Okay, so calibration aims at reducing the accuracy. So smaller accuracy means smaller deviation from the true value. And this is measured on all the possible values of all the possible measurable values of the quantity, which is from 0 in this case to this point at which the transfer function ends. This, in the context of measurement and of sensors, this maximum variation of the stimulus is called span. The span of the stimulus. In Italian, it's typically called fondo scala. I have a few additional definitions, but let me use all of them, because in this way we are free to use the word. Another common concept is hysteresis. In Italian it would be hysteresi, with an accent on the first E. And it's pretty easy to define. The issue is that sometimes the transfer function depends on the direction of change of the stimulus. So for example, when the stimulus increases, this is the transfer function, But when the stimulus decreases and goes back to 0, the transfer function does not retrace the initial points, but has a different path. This is, of course, something that leads to an error, because, of course, if you have a sort of stimulus S bar, for example, then you measure the signal here, and you do not know whether the stimulus is this one or is the other corresponding to the other direction. And this is typically, in principle, is close to the accuracy. It, of course, limits the accuracy of the system, and you actually want the hysteresis of a sensor as small as possible. By hysteresis, in practice, we define the maximum variation between the two curves. So this would be H, hysteresis, is the maximum error on the stimulus. Let's say depending on the direction of stimulus variation. So we typically need to define the hysteresis by, let's say, varying the stimulus in all the span, because when you vary from the minimum to the maximum of the span, you obtain the highest hysteresis, and then you measure the maximum difference. Again, these have all these quantities, the hysteresis, the accuracy, and the sensitivity, are all part of the information which is contained in the datasheet of the sensor. Non-linearity is another quantity with specific meanings. It is, of course, only relevant for linear transfer functions. Because, of course, it gives me information about how different is the actual transfer function from the linear nominal one. The point that we need to stress here is that there are different possibilities in terms of definition. Let's assume that this is the actual transfer function. Of course, is almost linear, but is not exactly linear. So this is the actual transfer function. And what we can typically do is the following thing. We can, let's say, evaluate the maximum error with respect to a nominal linear transfer function. For example, this is the nominal linear transfer function, and in this case we can define the maximum error. For example, it is more or less here. So we can call it N1 nonlinearity, and 1 is the maximum error with respect to the nominal linear transfer function. But also the other possibility is to make some sort of calibration, and therefore, for example, obtain a sort of let's say yeah. Ok, facciamo così. Okay. Then what I can do is, for example, extract a linear transfer function which has the maximum error with respect to the actual transfer function. For example, a line like this. And for example, in this case, for the drawing that I did, the maximum difference is here. So this N2 is the maximum error with respect to the best linear transfer function. Best between brackets linear and basically I can adjust the nominal transfer function in order to minimize the error. And of course, in this situation, N2 is always smaller or equal to N1. And or I can do some other calibration. Let's say these two are the most important ones. In principle, I can have less degrees of freedom and, for example, change only the slope or the intercept of the nominal transfer function, and in this case, I can reduce somewhat the error with respect to N1, but not really reach N2. So I can obtain an intermediate value. Yeah. So nonlinearity is very close to the accuracy, but it is specific to linear transfer functions. For linear transfer functions, linearity and accuracy basically are the same thing. Okay, so I want to finish with other, let's say, common words which have a precise meaning in the context of measure. One is precision. Precision means something different, for example, than accuracy, while, for example, in normal language, in common language, the meaning would be very close. Precision in the context of a sensor is something related to the repeatability of the measurement. So is the maximum error that we can make in the same condition for the same value of the stimulus. By error, I mean maximum variation, okay? Please follow me in this definition. So a measurement can be extremely precise, but with low accuracy, with poor accuracy, which means high accuracy. For example, if a sensor always measures in the same conditions, the same quantity, it is absolutely precise, but the quantity can be different from the actual value, from the true value. Okay? So precision is really connected to the repeatability of the measurement. Of course, what can affect precision is precision can be affected by noise, by memory, and by aging. So all things that lead to a non-repeatable transfer function. Okay, of course, noise, it's easy to understand the impact of noise on precision. Aging is, of course, also pretty easy. When a sensor ages, it can measure a different thing, whereas the stimulus is identical. Memory is a different concept, and it depends, for example, on the hysteresis, in the sense that for the measurement can depend on the previous variation of the stimulus, as we have seen in the case of hysteresis. So the sensor has some memory in the sense that it provides a response, a signal, which really depends on not only on the present value of the stimulus, but on the previous ones also. Hysteresis is a typical case in which we have a sensor with memory, but it's not the only one. Another concept is resolution. The resolution of a sensor is easily defined as the smallest increment that can be sensed. Smallest increment. Of the stimulus that can be sensed. Of course, when I say sensed, of course I mean measured. Okay. And finally, and this is the last one, we have the concept of reliability. Reliability is not a precise concept, does not have a precise definition, because there are different ways in which reliability is quantified. So the general meaning is the one that we would have in common language, which is basically the capacity of the sensor to work without failure. So a sensor is reliable if it can work without failure. Capability, not capacity, capability of the sensor to work without failure. Of course, in this term is a very qualitative concept. If we want to quantify the reliability of a sensor, we typically must express the reliability in probability terms. Okay, it's the way it is typically done. And in terms of probability, there are two quantities which are commonly used. One is the so-called medium time MTBF, between failure. Medium time between failure, and typically this is done at max temperature, at the maximum temperature at which the sensor is advised to operate. It's clear that it is a statistical quantity. And the other, let's say, complementary quantity that is provided is the percentage of properly operating sensors after specific time at maximum temperature. So, for example, I can say for let's say an accelerometer that after 10 years of operation at 150 Celsius degrees, 95% of the sensors are still operating. Okay, this is very similar to this one. Of course, one cannot know exactly what is the relationship between the percentage of properly operating sensor, and the medium time between failure, unless one knows exactly the distribution of failure times. Okay, so it really depends on the distribution, and typically distribution is different for different type of sensors, and there's a whole literature on how to investigate these things. In production, it is something which is extremely important. In our case, it's important to know that these are the quantities that typically used to express the reliability. One thing that I think from a cultural point of view it's useful to know is how these things are actually obtained. Because when I say, okay, after 1,000 hours of operation at maximum temperature, 95% of the sensor still works, one has to, let's say, interrogate himself or herself about how long does this test take. And typically, the way these tests are done is in a condition of so-called accelerated aging. And this consists in the following thing. One puts the sensor in a condition in which aging is accelerated, which means, for example, operating the sensor at higher temperature or at higher current or at higher voltages. And then one needs to have a model, a verified model, of how this accelerated aging is, the results at accelerated aging can be transferred to operation, normal operation at maximum temperature. So depending on the physical process, physical process for the operation of the sensor and the physical process for the damage of the sensor, we know how to correlate these few things. So these are obtained from accelerated aging tests. So this is pretty critical because one needs to know and one needs to be confident that the accelerated aging tests, and therefore these numbers are applicable to the conditions in which one wants to use the sensor. That is pretty, and it really depends a lot, and there are several types of applications. This is extremely critical for critical applications. For example, for sensors on electronic medical equipment, for sensors in electronic systems that has to be in the space or on airplanes and so on. In those conditions, failure is critical, but also the aging can be different. And this must be taken into account. Okay, so the purpose of this lecture was just to, let's say, introduce a few of these concepts, and then what we are going to do now is to make a break and then to consider some specific sensors and to look at their operation. So let's make a break and then we, let's say, restart in 20 minutes.